Welcome to today's Explainer. Okay, let's dive right into this. Whenever I watch someone tackle the Moab 240, running for literally days straight through some of the most extreme terrain on Earth, or finish back-to-back Ironmans, I just think, how? How does the human body actually withstand that kind of absolute, unrelenting punishment? We so often chalk it up to sheer willpower, right? Just grit and grueling practice schedules. But the sources we're digging into today reveal a much deeper, highly scientific story. Today, we're exploring the literal biological architecture of infinite endurance. We're going to map out exactly what is happening under the hood of the world's most tireless athletes.
I think anyone who pushes their limits knows that specific kind of pain. You're deep into a brutal VO2 max interval session, or maybe you're really pushing your lactate threshold during a marathon attempt, and your entire system just starts screaming at you to stop. But as our source text perfectly and honestly kind of bluntly puts it, while you're gasping for air after a mile, some humans are just getting started. I want you to really let that sink in for a second. This isn't just about someone having a slightly better cardio base than you. No way. We are talking about a striking, fundamental discrepancy in how human bodies process extreme physical stress. The answer doesn't just lie in how many miles they run, it's hiding deep within their cellular structure.
Now, what's really interesting here is that we're looking at a literal glitch in human DNA. The research defines this biological glitch as a specific anomaly, a mutation that drastically alters your normal physiological limits. Now, when you hear the word glitch, you probably think of a system error, a mistake, but in the realm of elite endurance, this is an evolutionary superpower. It completely rewrites the standard rules of exhaustion. What's so fascinating is that this anomaly allows these athletes to essentially bypass the brain's central governor. That highly protective mechanism that normally forces the rest of us to shut down so our organs don't fail. They just push right past it.
Let's put this into perspective. When an average runner's energy reserves start to deplete, their system rapidly hits a brick wall. Acidosis builds up, the muscles completely fatigue, and the body literally forces you to stop. But elite endurance athletes? They're operating on a completely different biological operating system. They possess a specific genetic marker that fundamentally delays this exhaustion. They aren't just, toughing out the pain better than we are. Their bodies are experiencing the physical toll of the run in a radically different way. That internal cascade that shuts you down simply isn't triggering for them at the same threshold.
And scientists have actually isolated the exact culprit behind this. It's the ACTN3 speed gene. Think of this as the master switch in an athlete's cellular makeup. This gene dictates the production of a very specific protein, alpha-actinin 3, in the muscle fibers. And its presence, or variation, fundamentally changes how those muscles fire, how they recruit fast-twitch versus slow-twitch fibers, and how they conserve energy under extreme duress. It is the literal code written into an athlete's cells that determines their metabolic efficiency at a foundational level.
Let's move on and see how this actually builds inside the cellular engine, because this is where the science gets incredibly dynamic. We're talking about extreme mitochondrial biogenesis. Basically, elite endurance athletes possess an exceptionally high oxidative capacity because their genetic blueprint allows for a massive, highly efficient density of mitochondria, and right alongside that is their hyper-efficient lactate clearance. For most of us, intense exercise causes lactic acid to build up super fast, dropping the pH in the muscles and causing that awful, burning acidosis. But for these elites, their biological mechanics act like a high-speed shuttle system, clearing out and rerouting that lactate incredibly fast.
Because of that immense oxidative capacity and that rapid lactate shuttling, this brilliant biological hack occurs. Exhaustion is literally transformed into fuel. Instead of shutting the whole system down, these cellular mechanics leverage processes like the Cori cycle. That's where the liver takes that lactate and converts it right back into glucose. So, while lactate is a suffocating byproduct for the average athlete, it's what stops us. For these elites, it becomes a secondary carbohydrate source. They are dynamically drawing energy from the exact same physiological processes that force the rest of us to collapse. It's like turning your car's exhaust fumes right back into premium fuel, an engine of infinite propulsion.
So the crucial point we have to pause and ask is this ultimate human question of genetic destiny. Is elite endurance simply a gift of birth? We just spent the last few minutes looking at how a specific gene and these microscopic cellular mechanics create this hyper-efficient state. It really begs the question, right? Are our physical limits entirely predetermined from the moment we're born? Are you either born with this incredible DNA glitch, or are you just destined to always hit that wall? This presents us with two fascinating, competing realities. First, you have genetic destiny, the hard truth that the ACTN3 blueprint, that baseline cellular advantage, is inherited at birth. You can't just change your fundamental DNA. But then there's built endurance. And this represents the incredible potential of the human body to actually alter its own physiological state. Through the science of epigenetic adaptation, relentless, highly targeted training can actually switch certain genes on or off over time. So actually, maybe you don't have the ultimate genetic glitch on day one, but through deliberate stress, you can optimize your own mitochondrial density, fundamentally improve your lactate shuttling, and literally mimic that elite advantage.
Which brings us to the final provocative challenge derived from our sources today. Can you actually re-engineer your own cellular limits? Knowing what we now know about the mechanics of exhaustion, the Cori cycle, and epigenetic adaptation, how close can you push your own biological architecture to that state of infinite endurance? Next time you hit the wall and your brain is screaming at you to stop, ask yourself, is this my actual hard-coded biological limit?